Basic electricity for appliance technicians. It is important to understand electricity basics when servicing appliances. After all, you will need to electrically troubleshoot them sooner or later. You don't want to be the technician that encounters a simple electrical problem and be unable to complete your diagnosis. If you have even a simple understanding of how voltage, current, and resistance act in a circuit, as well as the main differences between 240 volt and 120 volt appliance circuits, you'll be a more effective technician. In this video, we'll talk about voltage and current using the water analogy, Ohm's law, and talk a little bit about wattage. Appliance voltages and configurations. We'll discuss how 240 volt appliances are typically wired and configured, as well as 120 volt appliances. Troubleshooting techniques for 240 volt appliances. Troubleshooting techniques for 120 volt appliances. How to properly connect 240 volt appliances. Some of the mistakes that technicians and installers sometimes make when connecting them and how to correct them. Electrical troubleshooting equipment that technicians should possess when they're out in the field and some recommendations regarding that equipment. Lastly, there will be a quiz with answers and explanations to help solidify what you learned in this video. So what is voltage and current? You've heard the terms before, and sometimes they're even used interchangeably, but they're definitely not the same thing. Voltage is the force or pressure that pushes current through a conductor like a wire. It is always measured as the difference between 2 points. Without voltage, there would be no current. Current is the rate of flow of electrons that are being pushed through a wire by the force of voltage. You've seen the simple water analogies. From a conceptual standpoint, they are very useful in understanding how voltage and current work. In this image, you have two water tanks with pipes that release the water. The tank on the left is 5 feet off of the ground, and the one on the right is at a height of 10 feet. The higher water tank puts more pressure on this water column because of the additional weight of this column. This is analogous to a higher voltage level above ground potential. Thus, the water flows through this pipe at a higher rate than through this pipe right here. The faster rate of water flow, and thus increased volume of water, is analogous to current. All electric circuits have loads. Loads do work by producing heat, motion, or performing other functions. The simplest type of load is a resistor, such as a heating element. When current passes through a resistor, a voltage appears across it. That resistor is analogous to a bottleneck in the pipe in the water analogy. The bottleneck impedes the flow of water and causes a pressure difference between the left, as in this image, the left side, and the right side. And as you can see, the water is backing up on this side as it tries to be forced through this bottleneck in the pipe. This pressure difference is analogous to a voltage drop across a resistor. This is somewhat of an equivalent circuit of that water analogy. This resistor takes the place of that bottleneck that we just discussed. The pressure difference is now a voltage difference. Based on the voltage difference, the voltage drop across this resistor is 5 volts. The green dots represent the amount of charge that is being backed up on the left side of the resistor and the less amount of charge that is on the right side of the resistor. We've added an additional resistor over here because the return path is going to be at a 0 volt potential. That is because as this pressure, analogous to pressure, is reduced through each resistor, the pressure at this end is 0 because the electrons are being pulled into this side with the same amount of force that they're being pushed from this side. Notice also that each resistor has a 5 volt drop across it. In a circuit such as this, with more than one load, such as 2 resistors, some of the voltage drops across resistors will always be equal to the supply voltage. So we have 5 volts here, 5 volts there, and a 10 volt supply voltage. If we had just one resistor here, the voltage drop would be 10 volts, and that would be equal to the supply voltage. A simple formula based on Ohm's law, on the Ohm's law triangle, gives you a predictable relationship between voltage, current, and resistance. This image takes the previous equivalent circuit a step further by using that Ohm's law triangle to determine the current through the circuit. Using Ohm's law, if each resistor is 1 ohm, then the total circuit resistance is 2 ohms. That's how series circuits work. You add all the resistances in the series, and that gives you the total circuit resistance. So we have a total of 2 ohms in this circuit. If we use Ohm's law, we can now calculate the current going through this circuit. If you want to find current, you just cover up the I, and that gives you voltage divided by resistance. But we know the total resistance is 2 ohms. We know the voltage, that's our supply voltage of 10 volts. So we take the 10 volts, divide that by 2 ohms, that's going to give us 5 amps. Now, with that 5 amps, we can actually find out what these voltage drops are across each resistor, which is something that actually occurs all the time in electrical circuits. So if you want to find the voltage across this resistor, well, you know that you have the current and you know you have the resistance. So the voltage is equal to current times resistance. Current is 5 amps, the resistance is 1 ohm. That gives you a 5 volt drop across this resistor. Same with this resistor. This is the 1 ohm resistor. We have 5 amps going through it, and it's going to drop 5 volts. If you notice, the voltage here and there, again, is equal to the supply voltage. If we had only one resistor here, if it was say a 1 ohm resistor, you would have 10 volts across 1 ohm resistor, you'd have 10 amps. Then if you wanted to find that voltage drop across it, you would have 10 amps times 1 ohm, and that would give you 10 volts. So the voltages across each of the resistors in a circuit like this is always going to add up to the total supply voltage. If you had 3 resistors here, no matter what the voltage was across them, you were going to have a total of 10 volts across all those resistors. Now these two are not always going to be the same. If this was 2 ohms, then this voltage would be higher. The highest resistance always has a higher voltage drop across it. And we'll talk about that more in this video. Now let's talk a little bit about wattage. Heating elements in dryers and ranges produce heat. Heat is directly related to power. Power, also referred to as wattage, is the rate of actual work done by a load. Wattage is very easy to determine. Looking at the diagram, we can see that the power produced by a 10 ohm element with 240 volts across it is 5,760 watts. We can calculate that by using this formula right here, which is simply V squared, or 240 volts, times 240 volts, divided by 10 ohms, gives you 5,760 watts. Now, power is kind of a funny thing, because if you notice, we have a V squared right there. That means that if you reduce this voltage to 120 volts instead of 240, in other words, you're dropping it in half, then the wattage is actually going to end up being 1/4 of the original wattage. That's because of this exponent right there. So V squared over R. So if you were to take 120 volts times 120 volts and divide it by 10 ohms, that's going to give you 1,440 watts. Which is why in a dryer or a range, if for some reason your elements end up with 120 volts across them, instead of 240 volts, they may seem to run more warm than actually hot. It's not very intuitive, but that's how it works. Now let's talk a little bit about appliance voltages and configurations. In the United States, most 240 volt appliances adhere to a common arrangement in the way that they power loads and controls. 240 volts is advantageous for electric heating because, as we discussed previously, elements can produce 4 times as much heat at 240 volts than they can at 120 volts. An electric dryer primarily contains 2 120 volt circuits and 1 240 volt circuit. The main control and the motor are in this 120 volt circuit, which is derived from the difference in voltage between L1 and neutral. So you have your control here, which is powered by this 120 volts between L1 and neutral. You also have your motor. You can see this is where the circuit for the motor is. It goes through that relay into L1. So it starts at L1 and actually returns back to neutral. Neutral is your return path. Now the heating element is on a 240 volt circuit. As you can see, if we follow L1 through here, through this relay, and through the centrifugal switch of the motor, through this element, we'll end up back to L2. We will end up at L2, which is the return path. Or if you started here and went the other way, then L1 would be the return path. So the heating element is strictly on a 240 volt circuit, whereas the motor and the control board are on a 120 volt circuit, which is usually derived from the voltage difference between L1 and neutral. For an electric range, the control board, again, is powered by the voltage difference between L1 and neutral. And this is your neutral going to the control board. The return path is neutral for that. Now, there are relays typically on electric range control boards that act as switches that complete the circuit between L1 and L2 through either the bake element or the broil element. So you've got two 240 volt circuits here, one from L1 through that relay, through the bake element, and back to L2. You have another one that goes L1 through this relay, through the broil element, and back to L2. Now, typically there are other safety relays in here, but these are simplified drawings to make it easier to understand. Now, for what is typically 4 cooktop burners on an electric range, you have individual switches. Now, these aren't just switches, they're actually called infinite switches, which control the amount of time that the voltage is actually passed on to these elements. But they're just representative switches here for simplicity. And that circuit, those circuits go from L1 through the element and back to L2 for each of these circuits here. So let's take a look at 120 volt appliances. So with some exceptions, most gas ranges and dryers use only 120 volts. Heat for cooking and drying is produced by gas combustion. Thus, there is no need for 240 volt supply in most cases. Notice that the voltage to the gas dryer is derived from L1 to neutral. So you're just going to have a power cord that has a ground, a neutral, and an L1. The gas dryer consists primarily of 320 volt circuits: the main control, the gas and ignition circuit, and the motor. The motor and gas circuit are each activated by relays on the main control. The gas circuit also relies on a centrifugal switch in the motor to complete the circuit. This increases the probability that the blower will be pulling the flame through the funnel. The gas range will typically consist of 4 primary circuits. You've got your control, your gas bake circuit, the gas broil circuit, and then your spark module, which has 4 sub-circuits, each controlled by a switch behind each burner knob that activates the spark module. Note that when a switch is closed for a particular burner, all the burners will actually spark. The gas bake circuit is energized by a relay that is on the control board. The gas broil circuit is also energized by a relay on the control board. Note that there may be safety relays in here, but this is just a simplified circuit diagram. Troubleshooting 240 volt appliances. Diagnosing 240 volt circuits is easiest when you avoid referencing ground and neutral in your measurements. This is because the circuit that involves the 240 volts, as discussed before, does not include neutral. It actually ignores neutral and ignores ground. So neutral is not involved in the circuit and is not the return path. The return path for L1 is L2, and for L2 is L1. Note that L1 and L2 are of opposite polarity. If you were to measure L2 from neutral, yes, you would get 120 volts. Now, if you tried to measure L1 from neutral, you would also get 120 volts. Let's take a dryer with no heat, for example, and the reason it had no heat is because it lost L2. It lost this line voltage because maybe it had a loose connection at the terminal block or at the receptacle of the wall. The dryer would still run because all you need is 120 volts from neutral to L1 to power the control board and to power the motor. So this dryer would run, but it would have no heat. Suppose you went out on this service call and you decided to use neutral as a reference point to test for no heat. And this is why it's not really a good idea to do that. What you would do is if you did this, you would measure from neutral to L1. if you measured from neutral to L1, you would get 120 volts as expected because you do have 120 volts there. Now, since this dryer is missing L2, when this relay is closed and the centrifugal switch is closed, L1 is going to make its way through that relay, through that centrifugal switch, through this low resistance element and make its way all the way to L2. So when you get your meter and you're using neutral as a reference and you measure L2, you're going to measure 120 volts. And you're going to think that you have proper voltage at your terminal block when actually in reality, you do not have L2, you only have L1. Most field meters, multimeters, do not have the capability to distinguish between L1 and L2 because they're of opposite polarity. To actually distinguish the difference between L1 and L2, you would likely need an oscilloscope to do that because these two are what's known as 180 degrees out of phase. So that's why it's really not a good idea to one of the many cases in which it's really not a good idea to reference neutral when you are testing when you are troubleshooting 240 volt circuits. Now, how would you troubleshoot a circuit such as this, where this range has no broil? Everything works on this range, bakes and everything, but it just won't broil. But you've already done the basics. You've checked over here, and you've got 240 volts from here to here. So you know that you have 240 volts available for the broil element. You've gone ahead and you've checked the broil element, the resistance, and it checks out. So the broil element is good. So now what do you do? So you suspect that there's an open circuit somewhere in here, but you don't really know what it is. So after doing those basics, there is a troubleshooting method you can use that I call the point-to-point voltage drop method. Basically, you're going to connect a reference lead right here, and you're going to go through the circuit, and you're going to check for voltage drops all the way to the circuit. And as soon as you find a voltage drop, you're going to go point to point through here. As soon as you find a voltage drop, you're going to know that the point just prior to that voltage drop is an open circuit. So let's apply that point-to-point voltage drop method on a specific scenario. Suppose you arrive at a customer's house with a 240 volt electric dryer with a no heat complaint. You do the basics. You check for 240 volts at the terminal block. You check the heating element. You check the thermal cutoff, a high limit thermostat, and the operating thermostat. All of them are good. The element has 10 ohms, and these all read about 0 ohms. What you don't know yet is that this motor has a bad centrifugal switch. This switch will not close when it's supposed to. The centrifugal switch in the motor is supposed to close once the motor gets up to a certain RPM. And that, again, is to keep the heater from coming on until enough air is being moved by the blower to sufficiently pull that heat off the element. So at this point, you suspect that there's either something wrong with the control board, maybe a relay on it, or the motor centrifugal switch. So what you can do is use that point-to-point voltage drop method. And here's that method specifically. You identify the circuit. After you've done the basics, you're going to identify the circuit for your target load. Well, your target load is your dryer heating element. So you've identified that circuit. This will be the circuit right here. It's going to go from here all the way down through here. You're going to set your multimeter on AC volts. You're going to connect one lead to L1 using an alligator clip. Right here, this is your reference lead. And you're going to trace step by step through the circuit from L1 towards L2, which is the return path in this case. You're going to watch the voltage. Good components, except for your target load, should read close to 0 volts. Once you reach 240 volts, the component just prior to your test lead is open and suspect. Now this is a live voltage test, so this is for either qualified technicians or technicians under the supervision of a qualified technician. You're going to start your dryer in heat mode. You're going to take the other lead, the one that is not connected to this terminal block, and you're going to go to point B, and you're going to measure the voltage there. Now in this scenario, you're going to measure 0 volts here because that centrifugal switch is open, which means that there's nothing to pass this 240 volts through here over to this part of the circuit. So you're going to take your lead and you're going to measure from here to here. You're going to get 0 volts. You're going to check this, you're still going to have 0 volts. You're going to check this, you still have 0 volts. You're going to check this, you still have 0 volts. What that has told you is that all of these connections are closed. The heat relay is closed, the operating stat, high limit, and the thermal cutoff are all closed. Well, you knew those were closed because you measured them with your own meter, but you weren't able to measure that because it doesn't close until the dryer is put into heat mode. So now you know that all these switches are closed, and that's 0 volts. Now what you should have in this case is you should have 240 volts right here, because the highest resistance, as mentioned earlier, in a circuit is going to have the most voltage across it. In this circuit here, if this centrifugal switch was closed, all these would be 0 ohms. So this would be the absolute highest resistance. So this would have 240 volts across it. But you go ahead and you take your meter and you check there, you still have 0 volts. Now, take your meter over to point G, and now you measure 240 volts. Now you know, and you have to measure 240 volts because you're actually connected directly to L2. Now you know that you have 240 volts from this point to this point, which means you have 240 volts across that centrifugal switch. It's impossible to have 240 volts across the centrifugal switch if it's closed. That means it has to be open. So in this case, what you would do is you would replace that motor. Once you replace the motor, then this switch will be closed and you're going to have 240 volts right here. And the element will have, as it should, since it is the highest resistance in this circuit, 240 volts across it. Now this is just one of many scenarios where you can use that point-to-point voltage drop test. I also call this test a brute force method because what it does is it forces failed components to reveal themselves. Troubleshooting 120 volt appliances. That can be done much in the same way as with 240 volt appliances. Suppose, in this case, that your broil circuit wasn't working. So you connect your reference lead to neutral, you come over here, and you check point B with your other lead. You should have 120 volts here in a working broil circuit if this is activated. But you don't, you've got 0 volts here. So you keep going, and you go over here to point C. And when you're at point C, you detect 120 volts. Well, you should because you're actually at L1 over here. So this tells you that this over here, this relay is open. It's not closing like it should. You have 120 volts across it, and you cannot have 120 volts across a relay that has closed contacts if those contacts are good. So that relay is bad, and this control board, in most cases, would need to be replaced. Now, some technicians actually replace relays, but that's an entirely different topic. So once this control board is replaced, then L1 will make it all the way over here. You're going to have L1 over here, and you're going to have neutral over here. So this is 0 volts, and you're going to have 120 volts. Now, there is some resistance in the gas broil circuit, and that's going to be, initially, that's going to be the igniter. And once the flame lights, the igniter is taken out of the circuit, and the resistance here is going to be the gas valve coils. And again, this will have the highest resistance in the circuit because this is 0 ohms over here. This is supposed to be 0 ohms. And you're going to have some resistance here. The highest resistance wins, and it's going to have all the voltage across it because it is a single element in the circuit and of the highest resistance. Let's talk a little bit about 240 volt power cord connections. This is a typical 240 volt appliance 4-wire cord configuration. On this lug here on the left, you typically have L1, which is the black wire, neutral in the center, and then L2 over here on the right. And you're going to have a ground wire, a separate ground wire that is actually bonded to the cabinet for the metal part of the appliance. For the older 3-wire connections, you have one of the outer wires is connected to L1, the center wire is connected to neutral, and the other outer wire is connected to L2. Also, there's a copper strap that is connected from neutral to a ground lug on the appliance, which effectively connects neutral to the metal chassis of the appliance. Now, these are just a couple of examples of how terminal blocks are sometimes incorrectly connected. In this case over here, you have L1 properly connected and L2 properly connected. You also have neutral connected to the center lug, which is correct. However, whoever installed this also installed or left this ground strap here, which connects neutral to ground. And also the ground wire is connected where it should be on the ground lug. The problem with this is that neutral and ground should never be connected together on the appliance. Although they are connected together in the breaker box, they should never be connected together at the appliance. What happens if you connect neutral and ground together, then neutral and ground will actually share the return path and the current flowing back to the breaker box, which is a safety issue. One of the other problems with this type of configuration is that if this was a dryer, the dryer would actually work, and the homeowner would be unaware of the safety risks that this connection posed to them. Here's another example of an incorrectly connected power cord. You have L1 connected properly, L2 connected properly, but you've got neutral and ground connected to the same lug, and the cabinet has no ground wire to it. Now, in this case, the cabinet is floating, which is very dangerous, actually. You have neutral and ground also that are sharing a return path back to the breaker box, which again is an improper way to connect it. It's against code because ground, again, is never designed to carry current on a regular basis. So this is another incorrectly connected power cord scenario in which the dryer would actually work, but the homeowner would not know that this is improperly connected. Now, there are other forms of improperly connected power cord connections, such as a neutral connected to L1 and an L1 connected to neutral. But in those cases where you have L1 and L2 that are misplaced, oftentimes the appliance will show symptoms that indicate that there's an issue. Now, there's a minimum level of electrical troubleshooting equipment that technicians should possess out in the field. And one of those would be a multimeter that has different functions such as voltage, resistance, continuity, current, diode check, frequency, capacitance, temperature, and low Z. Low Z is just a feature that allows you to put a load on a circuit when you're testing for loose connections in power sources, in voltage sources, and that can come in very handy. I recommend that you get a meter that has low Z. Now, there are multimeters out there, such as this one, that have all these features that you can get for a pretty decent price. So this type of a multimeter is something that I would recommend having out in the field because you probably will eventually use most or all of these features. And there is a link to a recommended multimeter in the description of this video. A non-contact voltage tester is something that I recommend technicians have. I use it all the time. The test for the presence of AC voltage above ground, and among other things, can come in very handy for doing point-to-point troubleshooting and you don't want to have to connect a reference lead. This is also very useful in just generally testing whether circuits are live, which can be a real time saver. There's also a link to a recommended non-contact voltage tester in the description of this video. So let's go through a quiz here to help solidify what you learned in this video. What is voltage? Is it the rate of flow of electrons through a wire? Is it the power that energizes a load? Is it the force that causes current to flow through a wire? Or is it what resists the flow of electricity? The answer, it is the force that causes current to flow through a wire. What is current? Is it the force that causes voltage to flow through a wire? Is it what resists the flow of electricity? Is it the rate of flow of electrons through a wire? Or is it the power that energizes a load? It is the rate of flow of electrons through a wire. What is true of voltage and current? Voltage flows through and current is just there. Voltage is a potential difference between 2 points that causes current to flow. Voltage flows as a result of a current difference between 2 points, or voltage and current are not related. The answer is voltage is the potential difference between 2 points that causes current to flow. Number 4, what does the height of the water in the water analogy represent? Current, resistance, voltage or pressure, the voltage or pressure level above ground, or a voltage drop. It represents the voltage or pressure level above ground. Number 5, what does the rate of flow of water in the water analogy represent? Voltage potential, current, resistance, or a bottleneck. The rate of flow of water in the water analogy represents current, because current is the rate of flow of electrons through the conductor. What does the bottleneck in the water analogy represent? Resistance, power, pressure, or current? The bottleneck in the water analogy represents resistance. Number 7, what does the pressure difference in the bottleneck represent? Resistance, power, current flow, or a voltage drop? As mentioned, that pressure difference is analogous to the voltage drop across a resistor. So if you had 5 psi, so if you had 10 psi here and 5 psi here, we can conceptually make an analogy between that and a voltage drop across a resistor, whereas in this case, it's a resistor with a 5-volt drop. So the answer is a voltage drop. Number 8, how does current behave in a circuit? It decreases as it reaches the return path. Or does it remain the same through the entire circuit? Does it increase through the resistors? Or does it drop across each resistor? Remember, current, as it flows through a circuit, remains the same through the entire circuit. That's because you can have pressure differences throughout the circuit, just like you can have pressure differences in the water analogy. But despite those pressure differences, the rate of the water flow coming out of the tank is going to be equal to the rate of water flow coming out of the output and landing on the ground. So that rate doesn't change, even though you can have pressure differences throughout the system. So the answer is that current remains the same all the way through the circuit. Number 9, in a circuit with more than one resistor, how does voltage behave? The voltage across each resistor is equal to the supply voltage. The sum of all the voltages across each resistor adds up to the supply voltage. The voltage across each resistor is unrelated to the supply voltage, or all the above. Well, remember, if you have a 10-volt source over here, and we calculated the voltage drops in this circuit using Ohm's law. Notice that the voltage drops across each resistor always add up in a series circuit to the supply voltage. So the answer is the sum of the voltages across each resistor adds up to the supply voltage. Number 10, you have 240 volts across a 10 ohm element. How much current flows through that element? 2400 amps, 24 amps, 12 amps, or none of the above. Remember the Ohm's law triangle. You can find current by covering up this I here, which represents current, and then you're left with V over R. That's voltage divided by resistance. So if you take the voltage and you divide it by the resistance, 24 divided by 10 is 24 amps. So the answer is 24 amps. Number 11, what is wattage? It is related to the rate of heat produced by a resistor when current flows through it, or it is the rate of work done by a load, or it can be calculated by V times I, V squared over R, or I squared times R, or all the above. The answer is all the above. Number 12. If a 10 ohm dryer element has 120 volts across it, it produces 1440 watts of heat. If you double that voltage, how many watts of heat will it produce? 2880, 720, 5760, or 0 watts? Remember, power is equal to these equations here. What do we have? We have voltage and we have resistance. So this is a formula we would use. It's voltage squared, or voltage times voltage divided by resistance. If you double that, you have 240 volts across it. Then you're going to take 240 times 240, divide that by 10 ohms, and that gives you 5760 watts. And again, that's not very intuitive because you're doubling the voltage and you're going from 1440 watts to 5760, but that's just how power works. So the answer is 5760. Number 13. What is the best reference to connect one lead of your voltmeter when you're using the voltage drop method on a 240 volt element circuit? Neutral, ground, L1 or L2, or none of the above? The answer is L1 or L2. You typically do not want to involve ground or neutral when troubleshooting 240 volt circuits. Number 14. Why should you avoid using neutral and ground as a reference when troubleshooting a 240 volt no-bake circuit? For the most part, neutral and ground are not part of the 240 volt bake circuit. By trying to measure L1 with respect to neutral, you may actually be reading L2 through another component. Or all of the above. The answer is all of the above. Number 15. What is the best reference to connect one lead of your multimeter to when using the voltage drop method on 120 volt gas range? L2, L1, ground, or neutral? The answer is neutral. On a 120 volt appliance, typically you're not even going to have an L2, and neutral is going to be your return path. You never want a reference to ground. Number 16. If you have a 240 volt dryer but want to use the voltage drop method to check the motor circuit, what is the best terminal to reference at the block? L2, L1, ground, or neutral? Remember, on a 240 volt dryer, the motor circuit starts at L1 and is returned through neutral. So this is your actual motor circuit. L2 is not involved in the motor circuit, although L2 does have a centrifugal switch. It does connect to the centrifugal switch. That is an entirely different circuit than that which supplies voltage to the motor for the motor to run. So the answer is, when checking the motor circuit in a 240 volt dryer, you're actually going to use neutral because you're only interested in the 120 volt circuit between L1 and neutral, which powers the motor. Number 17. What is one of the few instances when ground would be used as a reference when troubleshooting? Never, when a dryer produces no heat, when checking for a floating neutral, or when a motor won't start. The answer is when checking for a floating neutral. In most cases, you're not going to reference ground when troubleshooting because ground should not be part of any circuit in the dryer other than to just connect the chassis to the breaker box and ultimately to earth ground. Number 18. Why should ground and neutral be electrically separated at the terminal block with a 4-wire cord? Because they are intended to be part of separate circuits. Ground should not carry current on a regular basis because it minimizes the chance that the enclosure will become energized or live. The answer is all the above. That's it for this video. I hope you found it to be interesting and informative. Although learning how electricity works can be challenging, continual education and experience will greatly accelerate your knowledge. If you'd like to join our Facebook group, here is a link to it right here, or you can go to Facebook groups and type in the keyword the tech circuit. This is a link to our website right here. And this is a link to our YouTube channel. Thanks for watching.